Today's broadcast brought to you by soap. Let's use it, like always. And now, what you've been waiting for. The host with the most. The teacher who's got the eyes. 2 of them. I don't... Mr. Ludlow! Thank you so much for that lovely introduction. Lovely. Can we let's get that music down. Let's fade that out. There we go. Lovely, lovely to see you all again here. Now I know what you're thinking. Another video? That's right. Today we're here to talk about homework 906. After 5. Let's pull up that homework now. Button. Who's got the button? We want to hit this button, we think. Boom! Homework 906. Start AP review. Nah. But that's okay. You don't have to start it because we're going to start it. Quinn's leaving. I know you can't see her because the background's, but like, hi, Quinn. Hi, baby girl. Hi. She's here. Come on, right? No, come here, ready? Whoa, come here. Does she ever? Ah! She's like in my arms but invisible. Okay. I love you too. Now maybe lay down. That was weird. Anyway, 906. So it's an AP question. We're not trying to hide this. 2015, question number 5. You can Google it. 2015, question number 5, AP Physics Release Exam. Boom. Pops right up. So let's go through it. So I got this diagram, and what's really funny is we would have set this up in class because this is how you set these up. But like, we'll do it. We'll do it. The idea of this is it's a string and a pulley, and we did a lab with a pulley a long time ago, so you can probably remember that. So it's pretty similar to that, in fact. Sorry, I'm just checking the levels. And instead of we tied the string to the cart, right? So instead of doing that, I keep looking at the over here's like a little picture of my face, so I keep glancing. Sorry. But instead, now we're tying it to an oscillator. Basically, just something that's going to wiggle up and down is the basic idea. The one that I have, it's cylindrical, and it just has a little thing that goes. It's a speaker, but someone glued a piece of metal to it. And then they call it an oscillator and charge money for it. So now that's going to wiggle up and down. And what's going to happen is it's going to cause waves to go down, right? They're going to strike the pulley, which is dense, right? It's basically like a node, like it's tied on, and it's going to bounce back. So we have the opportunity to have waves being sent down, striking a barrier and coming back. We also have more waves we're keeping extending. I think it sounds like interference and reflection simultaneously, so that means we got standing waves. That's right, Bill. I don't know what Bill is either. So we have these 4 strings, and they're showing us to this, and they're all in the fundamental. Now, recap, if you remember from I put that image up, anytime we have the fundamental, so if we have like this is our string, and let me change the color on that. So if I have this string, okay, this is what's called the fundamental, or the first harmonic, for a standing wave that has fixed. So check out that diagram with the fixed. I would definitely look those up and sort of know those. They're pretty darn important. So that's the first one. So that means they all look like this. Now, just a quick recap for this. If I were to think about changing the pen colors on this is not that good. If I have the second one, okay. The second one looks like that guy. So if we were to talk about these two, right, and this is, make this real clear for a second, this, what I'm doing off to the side here, this is something else. So this is like extra. These two here have to have the same speed. They are the same medium, but they have different wavelengths, right? and they have different frequencies because they have to have the same speed. Okay. The only way you get these different setups like this, if you don't change the medium, right, which is not changing the speed, is you have to change the wavelength and the frequency. So that's going to be super important as we go into this problem. So we have the 4 strings here side by side, and we're trying to say which one. Sorry, just change the pen. Great. They're all at the fundamental. Now this is where, so if I'm reading this, they're all at the fundamental frequency. That makes me go, huh? So that means I know that they're all like this first diagram. But say they're all different frequencies. So they're all at their own fundamental. Now, for fundamental frequency occurs in a medium. And if you change the medium, it would have a different fundamental. So the first thought in my head, I haven't read anything. First thought in my head is that those 4 strings can't be the same. Something's different. Now, what could be different is it could be tension, right? One could be tighter than the other. But using our physics brains, and we look right there, they're all hung the same mass m off the edge, which means tension is identical in all of them. So something has to be different about the medium. Could be tension, it could be something, but it's not that here. So fundamentally, something has to be different about them. Ha! Fundamentally. Get it? Because the fundamental, you get it. You get it. And then it says it's some distance L. So I know for all of these, L is going to be half. I'm really not a fan of these pens. So I'm using a different version of OneNote. But I'm just not overly thrilled. Oh, I hit cancel. That's not how you get drawing. Whoa, whoa, whoa. Color thickness. Let's go one thicker. So, yeah, it's better. So all of them are going to be L equals half a lambda. So that means that lambda is actually 2L. So wavelength is 2L for all these. Different frequencies, so they have to have different speeds. And then all of a sudden, like, yo, check out this equation that I just happened to randomly give you. Anytime the College Board does that, that's a very nice way of saying this is what's important for probably most of the rest of the problem. And it's like, check it out. Now, if they're explaining it, they're saying where VT is tension in the spring, and M over L is the mass per unit length, also known as linear mass density. Hang on, let's decode that for a second. Linear mass density would be linear density, right? So that means it's just something fundamentally about it. So if a high linear mass density would mean that it's a very, very dense rope, or it's very, very massive per unit. So you think about 1 centimeter of rope, right? If I had like 1 centimeter of steel cable versus 1 centimeter of fishing line, the 1 centimeter of steel cable has a higher linear mass density, right? It's more dense. And if we're looking at this, if you know how these two things would go, so we're thinking about the speed it's going to travel, just to dissect this equation a little bit. Ft. So if tension were to go up, the waves would go faster. I think that makes sense, right? If the particles are under more tension, it's easier for them to wiggle the next one. If it's very, very loosey-goosey, it's like, whoa, but if they're like super tight, it's like, so I think that makes sense that those two are directly related, square root there, but if one got bigger, the other one would get bigger, just not linearly. And then mass linear density is in the denominator, which I think also makes sense. If it got more dense for the same energy, it's going to slow down. I think logically that should make sense. This M per L thing, by the way, because see how they're describing it outwardly like that, I'm going to keep that together and treat that as if it's one variable and not separate it, because that's how they're doing it, so we're going to do it the same way. What is different about the 4 strings shown above that would result in having different fundamental frequencies? Oof. They're different. Now, one way we could sort of describe this would be that we're saying, basically, you know, we have V equals F lambda, right? They all have the same wavelength, right? But different frequencies, so they have to have different speeds. That's a little bit mathy, I think. I think another way to describe it for us would be they all have different fundamental frequencies, right? Because they have different fundamental frequencies, there must be something fundamentally different about the ropes, right? It could be linear mass density, or it could be like a physical property. Now, the official answer key for this states that they wanted you to somewhere say that they all have the same length and have the same wavelength. We said that. Cool. Then they want you to reason that since the wavelengths are all the same, different frequencies mean different velocities. We said that. And then they want you to say, basically, for the third part, they want you to look at that equation, and the mathy way for us would be, if they all have the same tension, the only way to get different speed would be a different linear mass density. Would be the way we could get through it. However, the other thing that they allow, so look up the scoring online, it says like no. You could say that there's fundamental difference. So different linear mass density, different total mass, different thickness of the same material. So you could just say that fundamentally they're different materials. They're different linear mass density or the different thickness of the same material. But those are basically the 3 points there. Boom shakalaka. Great. Keep going. A student now graphs frequency as a function of the inverse of linear mass density. Will the graph be linear? Ooh, linearization question. Problem is, that equation that's there does not have frequency in it. But we know v equals f lambda. So we're going to take this equation and this equation and smash them together. So I'm going to get f lambda is equal to tension over linear mass density all under the square root. So I'm going to try to isolate this a little bit. Now this side, if we're trying to separate it out in terms of doing like our reverse linearization type stuff, it would be like ft under the square root, and then the other thing is 1 over linear mass density, but it's under the square root. Right? Remember, we're allowed to separate square roots out like that. Now if I want to try to just get f alone, which I absolutely do, this would be f, and this is equal to the square root of tension divided by wavelength times 1 over linear mass density, but that's all under the square root. Just to remind you of this, right, this is our y equals mx. So if we're looking at this, if I want this to be linear, then I'm going to graph frequency and 1 over linear mass density, but under the square root, right? So it says, the student graphs frequency as a function. Will the graph be linear? It won't. So this is my linear graph. That student is graphing frequency and inverse of linear mass density, right? Not linear. Okay, and you can see that by that equation. Now, scoring guideline for this, official from, oh, is that? What? I'm gone. Weird. 2 points for this problem from College Board. First point is for doing that, setting the two equations equal. Second point here is awarded for basically saying that it's frequency and the square root of that that would give you a linear graph, not just the inverse of linear mass density. Yo, linearization again, another problem. Glad we know it so well and we're rock stars at it. Great. Let's scroll. Part C here now. The frequency of the oscillator connected to string D, and it vibrates in its second harmonic. Oh no. And we want to mark and label the points on the string that have the greatest average vertical speed. Oh no. Well, I'm going to draw on this. So if we check here, let's count first. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I got 12 spaces. If we remind ourselves from a moment ago, this is the first harmonic, also known as the fundamental. This is the second. So it's got to look like that. But if I have this shape and I got 12 boxes, that means that's got to be 6, and then that's got to be 6 to keep it consistent. So 1, 2, 3, 4, 5, 6. So I'm going to have nodes at either end, right? And this is going to be like a way, and then dotty. So I drew that, and that's great. And for this, great. But then that's not, they're asking for the greatest average vertical speed. So basically, greatest average vertical speed. Super fancy way of saying what parts wiggle the most. The biggest wiggly spots, the parts that wiggle the most would be the antinodes, right? Or the yes des. The yes des. Yes des. So if we're thinking about our nodes being at the end, dead center in here, right? So here I have 1, 2, 3, 4, 5, 6 boxes. So 1, 2, 3, right there, right? That spot. And then 1, 2, 3, right there, that spot. those are going to be the antinodes, right? Or the points of greatest average vertical speed. Pagabs. Whatever. Label them like that. Now, see if I can show you this. Great. Their drawing. Oh, it just cuts this thing clean out. I was hoping I could just show this to you because I do not have it open. We got some work to do on this camera thing. Whatever. Their diagram, just to show you what their diagram looks like, if I just cut it down a little bit, that one. I don't know, buttons are pressed, sorry for that. Theirs looks like that, basically, where they're like, right here and right there, thanks for playing. So you could have got away with a lot less. You could draw it on there. 2 points here awarded from the College Board. Points are for any indication of the second harmonic. So any indication of the second harmonic at all, anywhere. And then the second point is for labeling the antinodes. Jeez. Pretty straightforward question if we think about this. I think the last part here is do you understand the harmonics? And that was unfortunately one of the video topics, and also in that image that I put up on Classroom. I think it's a pretty great image. A little bit of linearization, and then A is, do you know basic things about what's going on with waves? So if we look at a problem like this, realistically, we should be able to just knock this out of the park. Hopefully this helps with 906, and I hope that you're still doing well, and I'll see everybody real soon. Bye. 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 Bye.